Oops. I'm Sylvain Lebren. I will talk about the Apache Cassandra storage engine. So I work for a company called DataStax that is doing support for Apache Cassandra, but they actually pay me to work on the Apache project full time. So it's pretty good for me, and that's what I'll talk about. So I'll talk about three things. Basically, I'll start with an introduction to what is Apache Cassandra. For maybe some of you don't know what it is, so it's a distributed database, but I will tell a little bit more on that. And then I'll quickly explain how the data model work, and we'll talk about the storage engine. So how do we actually write stuff to disk and read it, and why we do it that way. So Apache Cassandra is a distributed data store, and it was created to handle large amount of data, okay? That's its goal. It's an Apache project, so it's an open source project. It's an Apache project since 2 years, February 2010. Before that, it was in the Apache incubator, but it's top-level project since 2 years. And actually, last October, we released version 1 of Cassandra, so we felt that it was mature enough to call it version 1, and as a matter of fact, even before the version 1, it was used in production in a number of companies, including some fairly large company with fairly large data sets. And so, yeah, to give you an idea of the size, largest cluster I know about is about a little bit more than 400 machines and over 300 terabytes of data for one cluster. So, okay, so Apache Cassandra is a database. So you have a client, you talk to your database, you do queries, so you store stuff and you get stuff. That's basically what it does, but it's a distributed one. So your database will usually have multiple nodes, multiple machines, we call nodes, and well, the goal is you can actually scale that. But one thing with the Cassandra, it's a fully decentralized system, so every of those nodes will actually run the same software, and each node will, no node will be specific. Okay, so it's completely distributed. There is no, master node and slave nodes. Every node is the same. It's also a replicated database, so when you store data, the data will be distributed, so not every node will have a copy of every data. That being said, data is usually replicated. So replication is built in Cassandra from the beginning. That's a native way it works, which means that every data will be actually replicated in more than one node usually. You can configure, you can choose how many times each data is replicated, and the database actually figure out where each data should go. It's also a durable data store because it's not an in-memory grid or something like that. We do persist everything to disk, so it's locally durable, but it's also replicated, so you actually get a very, very strong durability guarantees thanks to replication and the fact that we actually even take durability seriously locally. And one of the main things we want is it to be scalable. Scalable means two things. It means that you can add new nodes easily, and it means that when you add new nodes, the capacity of the cluster will actually scale linearly with the number of nodes. So the way you actually add a new node, well, you start a new node with the software, and you say, you configure a few IP address so that it can connect to the other nodes, and then you say bootstrap, and it will join. So we call it the ring, the cluster the ring, because the way we distribute things is by using something called consistent hashing, which considers the machine on a ring. But I won't give too many details on that, but you can check consistent hashing online. But so you ask a node to join, and it joins. Data will be redistributed during that operation, but it's all done under the hood, and as a client, you don't see that happening. Another thing is that it's fault tolerant. So it's built so that if a node fails, you don't see it. Well, hopefully the operator will see it and will replace the node at some point, but at least the user, the client, won't see the failure. And because it's fully decentralized, there is no single point of failure. So there is no node that if it fails, well, the whole cluster is down. Every node is the same, so every node can fail. It's also what we call highly available, which is a little bit of the same thing as fault tolerant, which is it tolerates fault, but it's really transparent. Even if nodes are done, you can still insert, sing, and get stuff. Obviously, if you replicate data only once and one node is done, you won't be able to access the data on that node, but usually you have more than one replicate, so you can tolerate some amount of failure fully transparently. Okay, and the last thing I want to say is it's data center aware. So it's built to know about data centers. So you can actually have a cluster that cross multiple data centers. You may have one in the US, you may have one in Europe, you can have more than that. And they will all form only one cluster, okay? But the cluster will still be aware of the data center. So what that means is you can, for example, do things like, I want to replicate data twice, but I want to be sure that there is one copy on the data in Europe and one copy of data in the US. I don't want to have two copies in Europe and 0 in the US, because the goal is if I lose one data center, I don't want to have problems. So you can do that. And the other thing is that replication is aware of that in the sense that it's optimized. So for example, if you have two replicas in the US and you write something in Europe, so I didn't say a client can connect to any node, and the rest is handled by the database. So how you connect to any node, whatever you want, and the database will route the request. So if you write in Europe and you have to, and you need to replicate that twice to the US, it will actually send only one copy over the Atlantic, and then it will write into nodes in the US. And even when you do an operation, you can actually ask the database to respect a given contract. So for example, what you can do is say, I want to write something, and as soon as the replica in Europe have acknowledged my right, I'm good. I'm okay that the replication in the US is actually asynchronous, because, I don't know, maybe if I post a story on something, I just want that when I refresh the page, I can see my update, but if it takes 1 or 2 seconds to get in the US, that's okay. They won't know that I did it that 1 second ago anyway. So, okay, that was basically what Cassandra is, but I won't talk too much of all this replication thing. What I want to talk today is how, there is a lot of documentation online on that, but what I want to say is what happened on those bugs when you receive a query. And before that, I have to say a few words about the data model. So first thing is not SQL. Okay, Cassandra is what we usually call nowadays NoSQL database. It's not, well, it's not necessarily completely opposed to SQL, but what it means is that it doesn't do everything that SQL does. In particular, it doesn't do transaction, it doesn't do joins. And the reason is fairly simple, is if you actually start to scale database and scale it horizontally on many machines, well, joins and transaction to a lesser extent are actually hard to do very fast, and so, well, we don't try. But what I want to say here is it's more than a key value store. I will give a number of examples. It's not just you put some value and you get it with a key. You can do much more important stuff, much more interesting stuff. And the data model is actually inspired by something called Google Big Table. So, Google write that database that they actually use internally, but they publish a paper like 2004, I believe. And they have a data model that look a little bit like that because the data model was inspired. It's not the same, but it's inspired. And it's what we call column family based, okay? But chooses a column family is kind of a table. So let's take an example, okay? Let's take an example. Let's say a very simple example. I want to, rewrite a Twitter clone, okay? I want to take over Twitter, and I want to store that in my database. So first thing I need to store is the user profile. User will create a profile. You want to hold the data for those users. So if you do that, you will first start creating a column family, so that the yellow stuff, my column family is called users. And what my column family will do, for each user, it will keep the profile of the user. So, column family is kind of a table. And inside a column family, you have rows. That's a row, okay? And a row has a key, which is the greeny thing, which is the row key. You can think of that as a primary key for the row, but we call that a row key, okay? And in my example, that would be a user ID. So that can be anything. That could be the email of the user, but in my example, I've taken some random user ID. As a side note, in a SQL database, you would usually use some auto-increment for user ID, but in a distributed database, auto-increment is a pretty hard thing to do, so you use other stuff, typically UIDs. And in a row, what you have is columns, okay? So a column is, a pair of a name and a value, okay? So the first name here is the column name, and Justin is the column value. So in a row, I will have a number of columns. So in that example, okay, for my user, I will store the first name, the last name, the birth year, and I can have more of that. And my column family will be composed of all those rows. So I may have another user. It will have a new user ID, and it will have its own properties. So first thing to notice here is that not every row need to have the same column in it, okay? My second user have an email, but the first one maybe didn't give me an email. So you can think that as a null, but the difference is we didn't define a schema for that. So it's a schemaless database, which means that if you want to add new property to user and you have 400 million users in your database, you don't have to do an alter table that will take days or weeks to actually work. So that's the reason why Cassandra actually has a schemaless, that's one of the reasons why it's schemaless. Okay, that's a fine example. That's a fairly simple one. So take another example. And so here I want to write a Twitter clone. So one of the things I want to do is to store the tweets that a user made. So what I want is when the user clicks on my tweets, I want to show him his tweets. And I want to do that in a chronological order. So I will create a new column family that I'll call timeline. And inside I will have rows. And for each user, I will have one row. And as my previous example, the row key will be the user identifier. So that's my Justin Bieber user here. And the user will do tweets. So when it tweets something, we'll insert a column. And the column name will be a timestamp. So it's 0. I will use 0, 1, 2, 3 because it's an example. But in real life, that would be a timestamp of when the tweet has been made. So I will associate the timestamp to the text of the tweet. Okay. Both names and column, both name and value in a column are actually byte array for Cassandra. So you can store everything you want in it. And in particular, you can, here I just store the text, but I could store the text and I could add an info on which device the tweet was done or anything. So you can do all that, but that's a simple example. And when the user do more tweets, we'll add the tweets. But what I want to notice here is that in a row, the columns are ordered. So there's an order in a row. The actual order for the row is something defined in the column family. So each column family will define the order of the column in the rows. Okay, in that example, I pick a reverse integer order, so that's something predefined, but you can actually write your own comparator. So there's some power coming from that, so you can do interesting stuff, but there always is an order. So when the user will do tweets, we'll add this in the chronological order. So as you can imagine, the interest of that is that if the query you want to do, and that's likely what you want, is ask what are the last 10 tweets that this user made, well, we're able to answer that very, very quickly because we just find the row for that user and just read data starting from that point, and that's it. So there will be like one seek, basically. And you can, other operation that you do is, you can imagine there is tons of columns, and you can do a slice of a row. So you can ask, what are the tweets for, 1 week, 3 weeks ago? Give me all the tweets that this user did 3 weeks ago. So things like that you can answer just because it's chronologically ordered. And so the second remark is that the row can actually have lots and lots and lots of columns. Okay, there's actually a limit on the number of columns you can have in one row, but that limit is 2 billion. So you can still put a number of things. When a user has 2 billion tweets, you can start thinking about solution to actually use maybe 2 rows for that user, but usually not a big problem. So yeah, that's the way you would use that's the basics. That's really is the basic of the data model. So you have kind of static information where every user will have some set of info, but then you can do much more interesting thing by using the fact that the rows are a number of columns that can be pretty large, and the fact that those are sorted, so you can do a number of queries very efficiently. We do have, I won't go into the details, but we do have more interesting stuff that allow to do modeling much more easily. So we have things like secondary indexes. If I take my first example of the profile, I can create an index on the birth year of the user. So if I do that, I'll be able to query, well, give me all the users that are born in the 80s, for example. Okay, and you can do that, the database will actually do that automatically for you. We have something called distributed counters. So, well, they are just counters, but because it's that distributed store, it's distributed counters. But it's basically using a column value. If you use that, it's a column value that just is an int. And instead of setting the value, you actually say increment the value by that many or decrement the value by that many. And you can do all of those, and the database will aggregate everything. And we have things like composite columns. So composite columns are, a column is just a name and a value, but in fact, because that can be anything, any byte array, you can actually stuff a number of information, both in the name and both in the value. So you can, for example, have a name that is composed of multiple components. And you can define the comparison so that it first compares the first value, and then the second one, and then the third one. And we have built-in support for that. Same thing for the value. As I said previously, you could have the tweet of the text of the tweet, but you can have in the value, you can have on which device the tweet was done and things like that. And you can put all of that in a value. So okay, that's what we have. And now what I want to talk about is, given this data model, how do we actually store things to disk? So what is the goal here? One of the goals of Cassandra was to, there is one thing that I'm claiming, you can disagree, but I'm claiming that writes are usually harder to scale than reads. And the reason is that if you write something, you have to write the data on disk, okay? But when you do reads, you can always put more caching. If you really want to scale reads, we kind of know to do that. We add more caching, or we add more, we duplicate data and we are more nodes to read. But you cannot do caching for the writes, because the goal is to actually write it to disk so it doesn't disappear. And you cannot, if you duplicate the number of nodes where you have your data for your read to have more read capacity, you're actually writing more stuff, so it's actually make it harder for the writes. So a lot of people were able to scale reads reasonably. It's not well simple, but the writes were sometimes a little bit harder. So what Cassandra tries to do is to make writes as fast as it can and say, well, we'll try then to, reads will be probably a little bit easier. And the second thing is that Cassandra is made to work on commodity hardware. So the goal is you take a lot of, you take servers, but probably not too fancy servers, and you put a lot of them, and that's the way you scale. That's not buying very expensive software. And so in particular, what you want to do is you usually will use spinning disk for that kind of things, because spinning disk costs, compared to what you can store, spinning disk doesn't cost very much. And the thing is that spinning disk is very bad with random I/O, so that's something to take into account. So if we want to, and if you do writes, you will actually do a lot of random I/O if you have to, modify your database. Your writes will be distributed everywhere on your data set, so you'll have to change your files everywhere. So the goal is to minimize random I/O. So how do we do that? We use something called log structures storage. And it basically works that way. So you have a node, it has some hard drive, some memory, and what we want to do is write something. So what we want to write is, well, a given column. So a given column is in a row. So what you give when you want to write something, you give a row key, K1, and you give a column, so C1 with a value V1. You want to write that. So I assume that it's in one column family. There would be another parameter, which is the column family, but let's say that I'm writing in one given column family for this example. So when we do that right, we actually do two things. We first write the data in something in a structure in memory that we call a mem table. So we write the column K1, the column C1 in the row K1, and the mem table is really kind of a hash map of the row key to the columns that it contains. So when the mem table is empty, I just add this new entry that for K1 I have column C1. And the second thing that we do is we do write the writes on disk, and we write it in something called the commit log. What the commit log do is, so in the commit log, we will write queries, write query, as they come. Okay, so the commit log is an happen-only structure. We always add stuff to the end. And because we do that, the commit log won't do random I/O. It will be sequential I/O. You just write stuff at the end. You don't have to move anything on the disk. But for that to work, you need to have the commit log to be on a separate disk so that it doesn't do something else, so that it actually do random I/O just to come back to the end of that structure. So that's Cassandra configuration 101. You put your commit log in a separate disk. You don't have to, but you won't get the same performances if you don't do it. So everything basically does it. And as we'll see, you don't need a big disk to hold those commit logs, because it will actually be removed, and you can actually control the size that it can take. So if you have a disk of 80 gigs, you can say, I don't want my commit log to be more than 80 gigs, and Cassandra will deal with that so that it doesn't become that big. And when we've done that, well, we're done for that write, so we actually acknowledge the client. We consider, well, for that node, data is written. So if there is a failure now, we do have the data on disk. So we have f-synced that data, and the node die, we'll restart the node, and what the node will do, it will replay the commit log. So it will just replay the insert that were in memory only and hasn't been really persisted yet to disk in a more structured on-disk format. So, all right. So we'll get more. We'll continue receiving writes. So of course we can actually receive writes for more than one column. You don't have to write one column at a time. You can write multiple columns at a time. In fact, you can actually write multiple columns in multiple rows at a time. But let's keep it simple. And so you write things. You can write 2 columns. So in the mem table, we'll add a new entry for K2. We actually added two columns for it. And in the commit log, we'll just write what we received. But one kind of important thing is that when we write in the commit log, it's atomic, or more precisely, we actually rack check some and everything to be sure that when we read the commit log, we either read one of those, well, maybe not call that transaction, with one of the mutation. We call it mutation internally. So we consider one mutation, we write it atomically in the commit log, which actually means that when you write more than one column, Cassandra do that atomically. What I mean by that is that if I write C1 and C2 in column K2, I have the guarantee that either both of the columns are persisted or none of them are. I cannot have the first one persisted and not the other one. What is true, though, is that we don't do that atomically in the mem table part, so it's not isolated. So it's actually possible, unlikely but possible, that a read may only see K2 with only C1, for example, and not C2. That's actually true of the current version of Cassandra, but the next version that should be out in like a month or something actually add isolation. So in next version of Cassandra, the writes will actually be